We've got Australia to invest millions in Great Barrier Reef restoration and protection. So if you haven't been following the news like associated with climate change, the barrier reefs are being affected a lot by the temperature changes in the water. It's killing the reefs, and that's where a lot of fish go to hide and reproduce. You've seen Nemo? Yeah, so there's a lot of truth behind Nemo. And they're a little concerned now. They've started to create some artificial reefs, where you drop in like old ships into the water and then the fish can swim in those. But they're still having a big problem with the barrier reefs. They're being hurt by the warming of the water. If the temperature of the water changes, what happens to the oxygen content? Yeah, the dissolved oxygen in warmer water decreases. That is, it gets pushed up into the atmosphere. So we're going to read a little bit today about heat and why that's important. Notes would be that heat has the symbol Q, right? So for 5 points, tell me what are the units for heat? Joules, yes, the units for heat are joule or calorie, right? And you can also see the formula for heat on page 520, where they have Q equals C times N times delta T. And they show you then in use where you have joules, kilojoules, calorie. So heat, right, that would be calories, the amount of heat that you're consuming. So when you eat food, basically you are consuming heat. Yeah. You want to think about it that way? In the book, Into the Wild, there's a story about a gentleman that wanted to go out into the wild and take some pictures. So he tells, this is actually a part of the story, which is kind of independent of the gentleman that goes to Alaska. And so he decides to go out into the wild. And he wanted to take people with him, but they wouldn't go. So he's a well-off person, and he gets out there. He took enough food with him in like boxes just to last over the summer. But he failed to, I guess, inform a pickup time. So he didn't tell anybody to pick him up. And the airplane flies over just to check on him, and he waves both of his hands up in the air. And what does that mean? That means help me. No, when you wave both of your hands up in the air, that means I'm okay, leave me alone.
Oh, but if you're like freaking out.
Yeah, supposedly there's a hand signal that says you need help, and he didn't give the proper hand signal, so the plane flew away. He didn't have any more food left over, so 2 months later he freezes to death and dies. This is what the book says, Into the Wild. So we're talking about that because heat, if you don't have any food, you're going to be what? You're going to be cold. You're not going to have any heat, right? So like if your furnace goes out, guess what you're not going to have? Heat. Do work, and what does work equal? Starts with the F. Force. Work equals force. Times. Starts with a D.
Depression.
Starts with a D. Traveling over a specific distance. So work equals force times distance. Potential energy is knowing how to store that safely. So in the future, Garrett, we will be in a hydrogen society because you don't have to heat water with it. You can get direct electricity. You don't have to have a generator or a motor. You don't even have to have a battery. All you have to have is a container with the hydrogen, lithium wire, or similar metal, and you can produce electricity. Now, the big problem with it is it's got a lot of chemical potential energy, and if you get hit in the rear end with let's say a semi, and the container like ruptures, and there's going to be a lot of flames because of that chemical potential energy. Lots of are out of carbon fiber because they're doing that right now with gasoline powered cars. So let's say we make a electric car out of carbon fiber, and we get it to where, let's say it weighs, I don't know, 500 to 1,000 pounds, right? What's going to be the problem with that?
Safety.
What safety?
Like when it impacts something. So there's just like.
No, if you're going down the highway at, let's say, 80 miles an hour, right, and there's a big wind gust, what could happen?
It's gonna move your car.
Could blow you off the highway. That's one of the problems with the car being too light. It can get blown off the road. Now, when we have these wind gusts, you know, we're going to have some storms this week. That's a little bit concerning. I mean, you know, you'd have to be aware, because you know how humans are. We don't really we like to take risks. We drive too fast, get blown off the road. Heat flows spontaneously from a warmer object to a cooler object. Why is that? Why does heat flow spontaneously from a warmer object to a cooler object? You ever heard of osmosis?
Yes.
Yeah.
What is osmosis?
Yeah.
Isn't it when the subject has more water, travels the liquid to the ocean west?
Very good. It is the movement of water from a greater concentration to the movement of water of a lower concentration. So where is water of great concentration?
The ocean.
No. Claire, where is water of great concentration? Osmosis is the movement of water from a high concentration to a low concentration. So where would you have water in high concentration?
Pond.
A lake.
Pond.
And where would you have water in low concentration?
Ocean.
The ocean, because it's salty. Yeah.
And it's big.
It's about the salt.
Oh.
So if you go and you get some salt at like a restaurant, you pour it on a table and you add a little water to it, see the water flows into
What
it.
if it's a freshwater lake?
Right. So basically, you have an abundance. The whole point here is that warm is abundance. Cold is not. So warmth has to do with more movement. And we tend to think of that as being abundant. Cold is you don't have a lot. That's why you put blankets on, because you're like cold. You have a lot. Lauren? Yes, and there's a lot of forest fires happening right now. Where are forest fires happening right now?
Prime place is California.
California? Where else?
Tennessee.
I thought it was Arizona. Did anybody hear about some forest fires in
They're
Arizona?
really hot. So they
Yeah,
Yes.
the windy conditions. They say we're going to get some tornado threats here on Thursday. Yeah, I heard tornado threats on Thursday. Happening in chemistry, you have the system and the surroundings. Together, the system and its surroundings make up the universe, or the actual reaction you're observing. So you have to define which of these two are happening in the reaction. Why is the system and surroundings important? What does it determine? Raise your hand. 10 points. If you can tell me, what does the system and surroundings determine? Determines whether the reaction is what?
Oh, and
Starts with an E.
I learned this.
Electrons.
Exothermic or
Endothermic.
endothermic. What does exothermic mean?
It releases heat.
Right, so it releases heat. So if the system releases heat to the surroundings, then it is Cody. If the system releases energy to the surroundings, it is exothermic. If the system takes in energy from the surroundings, it is endothermic. That's why those two terms.
His fireplace.
Right, the fireplace. So he's getting heat from the fireplace. They don't show you that, but we're going to assume that's where the heat is coming from. Freeze, its temperature must decrease so the heat flows out of the water into the air. So that's going to be what? Play sport, you might have an injury in the future. The athlete is, what type of reaction is the athlete to the surroundings after he's worked out?
Exothermic.
Exothermic. So the athlete's releasing heat, right? Now, how about ammonium nitrate and water, like a cold pack?
Yeah.
Is that going to be an exothermic or endothermic reaction? Yeah, it's going to be what?
Endothermic.
Endothermic. It's going to take heat from you into its system. So if you're asking specifically about the cold pack, then the cold pack is an endothermic reaction, because it is the actual system and the surroundings would be you. So it's taking energy from the surroundings into the cold pack. Now if you're looking at it from the athlete, then it's an exothermic reaction. That is, the reaction in the body is releasing to the cold pack. So you have to look specifically at what the question is addressing. For water is 4.184 joules. Ethanol is 2.44. Water as a solid 2.03. That would be as an ice. And then you go all the way down here to like iron. So the heat capacity is the amount of energy needed to increase the temperature of an object exactly 1 degree Celsius. So for water, it would be 4.184 joules would be the heat capacity. Nova Science Now video on climate change. They were talking about how we know that water has such a high heat capacity that most of the energy being stored from the sun is being stored in the water, right? And you can see that specifically what we talked about at the beginning of the period with the Australia barrier reefs, how the water is increasing in temperature. So water has a very high heat capacity, and you can see that in the book right here. Now, this is very concerning for coal. I don't know if you know this, but what county in Kentucky is the largest producer of coal? Anybody know?
I knew this.
Starts with a U. Which county in Kentucky is the largest producer of coal? Clayton? You ought to know this, you live in Kentucky. Starts with a U. Eliza. What county in Kentucky is the largest producer of coal? Yeah, that produces coal. It's the largest producer of coal. Starts with a U. Union is faster in water than it does in air. And it's very similar when we look up here with a swimming pool. Whereas like when you're swimming, you go over to the ladder, you touch it, it's really, really hot. So the lava stays hot because air has a high heat, or has a low specific heat capacity. Air has a lower specific heat capacity than the water does. So just like the ladder, it's hotter, and the lava will stay hotter in the air. So keep that in mind. The barrier reefs getting warmer. They die, and then what's the problem with that?
We die. It's like a lot of species.
You ever seen Nemo?
Yeah.
What happens when the reefs die?
Everything around it dies.
Nemo doesn't have a place to hide from the big fish. So then it ends up being like bad for the fish population. If you don't know this, people like to eat fish.
And we die.
I like to eat fish. It's really good. Fried fish. I mean.
Chemical potential energies converted to the work of moving the pistons, which ultimately moves the wheels and propels the automobile. However, much of the chemical
And because water cancels out fire. That's good.
You're close. So the question is, why does lava cool faster in water than in air? Right now? What?
He's asking me how silver is.
Why does lava cool faster in water than in air? Now, if you look in your book on page 520, does everybody see page 520? You'll see the specific heat capacities. Water is 4.184. And let's just look at, let's say, aluminum is 0.897. Now, if you go swimming in a pool, right, in the summertime, you're swimming laps and the whistle's blown, it's time for a break, and you got to get out and you swim over to the metal ladder, and you touch it, and what do you say? Wow, that's hot, right? So the metal ladder will be hotter than the water.
I've never.
You've never experienced that? Well, try it one,
I
huh?
was on this. It's not.
Yeah, it's hotter than the water is.
It's not that hot.
Well, it's hotter than the water.
Well, like when I was on the swim team in like Georgia, we you swim during the winter, but we swim with the bubbles, so you have to come outside and be negative degrees outside, so it'd be colder outside than it was.
Okay, if you're in the summertime and you go and let's say you touch the automobile hood that's made out of, let's probably like aluminum, it's going to be hotter than, let's say, the grass, or hotter than wood. Yeah, metals tend to have a lower specific heat capacity. So you see right here, you've got aluminum and you've got iron, silver. These things heat up faster in sunlight with infrared energy. That's a characteristic of their composition. Make sense? Yeah, plastic as well has a different heat capacity than water does.
Is that why they say not leave like spray heat down?
Okay, so that goes back to the lava. Lava will cool faster in water because it has a very high heat capacity. It has the ability to absorb a lot of heat, whereas aluminum does not. It heats up very quickly. Specifically, the one we think most of would be infrared, and that would be on the electromagnetic spectrum energy, but you also have electrons. Electrons in the form of electricity, lightning, that would be energy, a light bulb. The fluorescent lights tend to be more efficient, have less energy loss, but electrons are energy. So electrons and photons, they're both considered energy, and if they didn't have mass, you wouldn't be able to distinguish between the two. Now up here it says energy has neither mass nor volume. Once again, if they did, you wouldn't be able to distinguish them. The reason why they say that is associated with they're difficult to measure. So the electron does have a mass, it has been measured, but the photon, the particle of light, has never been measured in an experiment. Maybe one day you will. It's very small, it's difficult to do, difficult to measure that, so we don't like to make assumptions. We don't like to make assumptions in science. Burn has been stored in the wood as Versante.
Chemical potential.
Graph. And the graph should have looked something like this. This is just kind of a review for you to see what you should have drawn on the cascade answer. The cascade graph had the heat of fusion and the heat of vaporization, and then you have where it was going to go up because the gas vapors will continue to rise as temperature is added. And then you got the heat of vaporization right here. Liquid and vapor in equilibrium, and then the solid and liquid are in equilibrium there. So it's going to take a little bit of energy, the absorption of it, for it to go to a vapor. And then you have right here, it's a solid at 0 degrees, and it's going to absorb heat there for it to become a liquid. Now once you have the vapor in this stage, it then has to release the energy. So water as a vapor has a lot of energy in it. So then that's going to be an exothermic reaction. So it's going to release that energy from the system to the surroundings. So ice, I guess you'd say melting, is a exothermic reaction because it's releasing heat to the surroundings. Does that make sense? You're releasing that to the surrounding. When it's the opposite, you're forming ice, you're trying to the opposite. No, system and surroundings. Because if you don't focus on this, you can get really confused very quickly. What are you talking about as far as the system, and what are you talking about as far as the surroundings? So if I put my hand on the ice, and I'm going to say my hand is the system and the surroundings is the ice, then my hand is exothermic to the ice. My hand is losing heat to the ice. Does everybody see that? Now if I'm talking about the ice being the system and the surroundings being my hand, then the ice is going to be endothermic to my hand. That is, it's going to be absorbing heat from my hand. So it's very important that you are clear as far as what is the system and what is the surroundings, because you can look at it two ways. The heat is going to flow from what? Heat flows from a great concentration to a low concentration. It's kind of like osmosis. Anybody know what osmosis is? Vance, what's osmosis? You didn't have biology last year? You studied osmosis? What? Yeah, osmosis is the movement or flow of water from a high concentration to a low concentration. That's osmosis, right? So, where would water be high concentration? Where? A lake. And where would water be low concentration? The ocean. And what makes it low concentration in the ocean? The salt. Very good. So if you have salt on a table, you add some water, the water flows into the salt. You want to move from an area of great concentration to an area of lower concentration. And why does it want to do that, Christian? Why does it want to move from area of high concentration to an area of low concentration? That is heat. Hot things want to move to things that are cold. Why? Balance, equilibrium, what does that produce? Huh? Stable. You'll understand that one day when, you know, things are stable in your life, you're like, oh yeah, this is nice. Stability tends to be a thing that you welcome. Balance. If you're out of balance, you're kind of like struggling a little bit. Might have too much weight over here on this side. You got 10 gallons of water over here and half a gallon over here, so you're kind of walking all lopsided. At coal-fired generating plants, that's where we still use steam engines. So that is a very primitive 1800s use of resources. We waste a lot of energy heating water, just like the lava. It cools faster in water because water absorbs a lot of heat. So every time you burn something and you just put it into water, guess who's not going to pay to heat the water? I don't want to pay to heat the water as the electricity consumer, right? I just want to pay for the electricity that comes to my house. But if they have to jack up the price of that electricity, then I'll pay more for it, which I don't want to do. So I want you to find cleaner, I guess you would say, more efficient ways of generating electricity. That's really up to you. If you can drive down the cost of electricity, guess what that's going to do for you? Allow you to have a retirement faster. And now, if you want to work till you're 70 years old, then just don't do anything about trying to make energy generation more efficient. But if you want to retire faster, if you want to retire like in your 30s, if you come up with a way to help, you know, decrease the cost associated with electricity generation, then consumer products will be a lot cheaper. Cars will be cheaper. Electronics will be cheaper. So forming ice is an exothermic process. You have the liquid, you have to remove that heat in order to get the ice. And this is what makes getting to absolute zero very difficult and expensive, because you have to have high temperature, high pressure that is, and you also have to have the ability to remove the heat, which is not cheap to do.